Good afternoon. Welcome to the next session of Computational Fabrication Seminar. And this week's session is about architected matter. I have with me two wonderful speakers, Kristina Shea and Chen. And this week we have a bit of a tighter time schedule since Kristina has to leave before the end of the talk. So any questions, please ask during her talk and they will be answered immediately afterwards. And otherwise you will be able to speak and ask questions to Tim after the talk, as usual. Kristina is a full professor for engineering design and computing in mechanical and processing engineering at ETH Zurich since 2012. And her diverse multidisciplinary research interests are focused on conceptual design methods with applications to the design of creative and innovative structures, active structures, consumer products, robots, space applications, automotive components, buildings, biomedical devices, and even more. So we are very excited to host her today, and Kristina, the floor is yours.
Thanks very much for the introduction. It's my pleasure to be here and to present to you some of our work in 4D printed tunable structures and machines. And this work was mostly done also in collaboration with Chen, who will follow this talk. So in my lab, what we do is we work a lot with new applications of 3D and 4D printing. So we were exploring additive manufacture and what it could do. And for example, started out by looking at aspects of geometric complexity and multi-material design, lightweight design, and then moved into what new things could we do with this? And this is where Chen's PhD work started. How can we use these new materials and embedded functionalities to create passive machines? And we also work a bit in aspects of customization and personalization. So for example, a 3D printed spinal disc that uses the multi-material 3D printing to be able to customize the design for a certain person. So we started off by looking at the tunability of multi-material 3D printed structures. And so the process that we use for all this work is the Connex machine. And so that provides a certain set of materials, and we were looking at how can we tune the elasticity in structures. So if we have these three lattices, they each are printed with a slightly different material, and you get a slightly different deformation. And this we can use to, for example, optimize lattice structures for the process. So either using the multiple materials in the lattice to be able to adapt the structure, and also looking at aspects, for example, of anisotropy in the printing to optimize for that as well. And so starting off from these lattice structures, we then quickly moved into 4D printing. This was also through an initial collaboration with Skylar Tibbetts, who coined the term. And 4D printing entails the multi-material printing capability of materials that are functional materials. So they transform over time. And the idea is that we can create structures and objects that change from one shape to another directly off the print bed. So without embedding new components into the structure. So 4D printing uses functional materials. The materials alter their physical properties over time, and they alter when exposed to changes in the environment. So for example, temperature is what we use mostly. So our goal was to be able to create and design passive machines that use these functional materials that are fully 3D printed. So we're getting rid of traditional actuators and power sources and sensors, and rather using energy from the environment to morph an actuator structure to create multiple stable states and multiple functions, and also have the structure be load bearing. So for example, the pyramid that you see in the bottom corner that I'll show later. So what this does is it changes the design problem into from a traditional mechatronics one into it's the design and the material that creates the machine. So rather than additional components. So what's the potential advantage of this? So why would we want to do this? So first, they're low energy. So they use the energy in the environment. So for example, temperature to create their actuation. They're lightweight. So we're not using traditional components like motor, electronics, or batteries or tethers to power sources. This means lighter weight. They're also more highly integrated. They're compact, so a deployable design leads to smaller transport volume and less assembly. So it's a deployable solar panel that you see in the image on the bottom right. And finally, they're reusable. So they can reconfigure themselves and provide this multifunctionality. So these are the advantages that I hope to show you. So with the PhD of Tim Chen, we started by, I asked him to design something that was flat and that could deform itself into, I think I said a pyramid, but he made a dome, which is great. And so what he did is he created the structure that has bistable joints. So these bistable joints are multi-material joints that when you apply a load, represented here just by the nuts here, they close the actuator. And so you could also open them. And so there's a certain force that's tunable to be able to close and open these actuators. And so this is also monolithically printed all together. So it creates this passive machine. And so these are the designs that he can create with this. So he can create networks of these structures with the bistable joints that are reconfigurable. And in the reconfigured state, it's stable. And they're also in the future, they're load bearing. And so from a simple design, a multi-stable reconfigurable design is created that can have these different states. So in our work, we also try to combine computational design. In this case, it was really just simulation via dynamic relaxation that was used to be able to model the different openings or closings of the bistable joint to create the different designs. So we can simulate the possibilities here. So the next step was then to be able to actuate these automatically. And so it turns out that these connex materials are shape memory polymers, which is highly advantageous for us. And so the next step was to add these shape memory polymer strips to be able to activate automatically the structures. So it's still the same bistable joint, but here it's activated by these black strips that you see here in the middle. And they can be designed such that the timing is such that the first opens, then the second, and then the third. And so that creates this passive actuation by temperature. And so the work we do uses the shape memory polymer quality of the connex materials by a programming model. And so the programming of a shape memory strip is different than computer programming. And what you have is you have a printed state, and then you heat it to the glass transition temperature, you apply a load, and then you cool it down in the third step. And then the final step is to recover it by heating it back up. So it's a very simple so-called programming process, but it's programming of the material. And we got a little bit lucky because these are the materials of the printer. And it turns out that the soft materials are down here. They have a low glass transition temperature. Then we have this one point of 30 degrees in the middle. And then we have a group, the rigid materials are a higher glass transition temperature. And so this is beneficial in the design to be able to use these different properties. So here's the design again. And so you have these bistable actuators that can be actuated by the shape memory polymer strip. And so you have, they can either be plus is, so they can be actuated, pulled out or pushed in. And then 0 is just the structure around, so it's not changing state. And what I think I want to bring out as well is that in these designs, it's a very, I still love the details of the design. So this is the middle joint. And these details is also what makes these designs work. So it really is the design and the materials in a very, I think, elegant way to be able to create these passive structures. So here what you see is the structure. It's in a temperature bath. It's in a water bath for the temperature. So not that it needs the water, but it just provides uniform temperature. And you can see it pushes out into a stable state through these shape memory polymer strips. It's load bearing, which was unique at the time when this was published. And it can also move to, I'll just fast forward a bit, can move to another state. And so in this state, it also carries a load as well. So these are these multi-state structures. And this was a big part of Tim's work. Another project that he carried out with Dr. Bilal and Professor Durayo at Caltech was to use the principles of this to create a deployable solar panel. So here's the solar panel. It compresses to 10 times. So it's again this a material programming aspect, and then it will expand out, and it's using a scissor mechanism on the outside, also with some shape memory polymers. So it expands out in about less than a minute. So it expands 10 times in less than a minute. There you can see the joints there and the rigid and soft materials next to each other. And here it's going up to a temperature of about 45 degrees. And so it's using the temperature to actuate. There's no single individual actuators on that. So the next example I want to show you in this area is 4D printing for shape morphing. So while I like to look at machines and creating passive machines in our group, the last two PhD students who worked on this topic looked at shape morphing. And the reason is that we wanted to go back and look at the computational design tools and methods that could be developed to help designers and engineers to create these 4D printed structures. And so we all know and like lattices. And so we went back to this saying, okay, if you had for example, a car body and you wanted to change the shape of that to improve the aerodynamic performance, so it changes shape in response to, let's say, pressure, that would be a nice application of 4D printing. And we actually had a project with industry on that. So it could also be a shape morphing airplane wing as well. And here the principle that we're going to use is a bit different. And so here are the materials, same materials I showed you before, and same glass transition temperatures. But now this work was done by Thomas Lumpe in my group. And what he did is looked at the change of the Young's modulus when you heat up the materials. So before we were looking at this glass transition temperature and the programming of the material. And now the switch is to say, okay, what happens to the Young's modulus and the compliance of the material as you heat the material? And so when you heat the material, what happens is you have so he's looking at these two materials, so the high temp material and Vero White, which is a rigid material. And you see here on the right-hand side that the Young's modulus, when you heat it, changes not uniformly between those two materials. So at this temperature, about 65 degrees, you get a big spread between the Young's modulus. And what he used is actually the 80-degree temperature, because it was just more reliable. These temperatures aren't exact when you're heating the materials. And there, the difference in the Young's modulus is 305 megapascals and 8 megapascals. So it's significantly different. And so he wanted to get rid of this programming step that was needed for the bistable actuators that Tim had. And so what he thought of is, okay, if we have a lattice structure and it's at a low temperature and we have a homogeneous stiffness, then what happens if we then add in some compliant members and some rigid materials? And in this case, we can then heat it up, and then we get heterogeneous stiffness. In the heterogeneous stiffness, then the structure will deform. So we apply a load, and then we get simple actuation and a desired deformation. So without programming individual members like you saw previously. So that was the goal. So this creates a different type of programming cycle. So we have a lot of structure. We heat it up, in this case to 80 degrees. We apply the load, and then we get the deformation depending on the distribution of the materials in the structure. We cool it down, it locks that into place, and to recover back to the initial state, we heat it back up again. So you still get this programming cycle, but you don't have to program individual members. So you program it all together. And so it became an optimization problem then to optimize the material distribution to achieve this deformation. And so the optimization problem is then we have a lot of structure. We're going to optimize for a given deformation U. Subject to the normal finite element equilibrium equations. These are just considered simple truss bar members. And what we have is we want to use these two materials and distribute them in the structure. And so he uses a penalty function to do this. And so he creates a optimization model in the initial case that's using gradient-based optimization with the penalty function to create the initial distribution. And then the second step is done by a genetic algorithm to then push the members in the structure towards the two different materials. And then you get the optimized structure. So I'll show you the results here. And in the results here, we have 3 different examples. So it starts with 2D on the left-hand side with 154 bars. Then we have 896 bars in the middle and 3,516 bars on the right-hand side. And you see the different distributions here if I click through. So that's the real structure, and the white ones are stiffer and the grayish or black ones are softer. And those are the 2 different materials distributed in the structure to create the deformation that was defined as the goal. And so he also 3D printed these and then experimentally tested them. The 2 on the left-hand side, so the 2D and the 3D lattice, are tested in an Instron machine using a temperature heat chamber in the Instron machine. And the one on the right-hand side, the airfoil, that's tested using a water bath for this uniform temperature. And so he was able to show with a good degree of accuracy that, that we can create these desired morph shapes in the structures by using not the shape memory effect of the material, but rather the difference in compliance when you heat it. Okay, so I'll just wrap up with a few conclusions and challenges. So what do 4D printed machines offer? They're low energy systems, so they're using, in our case, temperature, but they could also be activated based on other things like light or pH and so on in the environment. They're lighter weight and use less material in comparison to traditional actuated systems because we don't have the actuators, especially in the motors and so on. They also create a more integrated system in that way. They have a smaller print and transport volume. That's especially the case when we're printing something flat and then deploying it up. And they have multifunctionality and reuse and provide some new functionalities. So one project, new project in the lab is on the right-hand side. So this is a deployable polymer wave spring. And so this is printed flat. And then when it's deployed, also using temperature, it deploys into this wave spring. And then the nice aspect of this is then we get the fibers running along the spring. So we can create a complex object that's printed flat in this case. So what are the challenges that are left? The big challenges still exist in the printable functional materials. I hadn't thought when we started this project that we'd still be using these convex materials, and we're always on the lookout for better options. And they're slower to develop than I'd like, I have to say, especially in terms of the 3D printed options of functional materials. Computational design methods, one thing we're looking at in my lab is that how to create more generic computational design methods that can be used for applications, also used with different types of active materials. More complex tunable machines. So the example on the right-hand side of the polymer wave spring is just one example, but we want to continue this direction of creating these passive machines and to create more complex one. And finally, of course, industrial applications. And so in industrial applications, here are just some we've looked at so far. Automotive and aerospace, I think shape morphing of panels wherever they are is still a good opportunity. In space, so this is one that Chen showed in terms of a deployable solar panel. There again, we need the right materials that are space grade. In biomedical, we've also looked into that. And again, we need better biomedical materials. In buildings, one example is potentially a passive shading system that a PhD student is looking at currently in my group. And in robotics, so work of Chen, also with Professor Doraya, also showed a passive swimmer, and there are potentially more applications in robotics too. So I just want to conclude by thanking my lab and all of our collaborators. Of course, it's all their work that I've just presented, and thanks to them, and thanks for your attention.
Thank you very much for the talk. And we have a couple of minutes for a couple of quick questions. And the first question that I have is with regards to the monolithic manufactured materials. Did you investigate how often they can be actuated before they break? Are they durable?
Yes. So I used to have in this list of 4D printing challenges the either fatigue or reliability of the materials we have. So it depends on the design, of course. I think in Tim's examples, if I remember right, but Tim, correct me if I'm wrong, it's about 20, 25 times. And yeah, it really depends on the joint design. That's where, especially with the bistable structures, the joint design is so important. And so I love still looking at, I still have these models in my office. I love looking at the designs because I know the sweat and work that went into making these structures that can deform in that way. It's not easy at all. In terms of this, so this example is new, this polymer wave spring, and that's one of the studies he'll be doing this summer. Is one is the computational design for tunability, but also the to test how many times can it be used once deployed. Yeah, but it's a big question. We do our best with the designing with the materials we have, but I would still love better materials.
For this, I have a follow-up question. Are the materials sort of just designed by someone else and then you adapt them? Or do you also have some collaborations where you have what kind of properties you would like for the material and then ask material scientists if something like that could be developed?
Yeah, that's the direction I still want to go. We haven't so far. We've exploited what's available. And for example, the example on the right is it's actually a more, let's say, low cost multi-material FDM machine. So it has a lot of available filaments, which is, we're just starting to try out. I would like to do that still in the future. We've tried some smaller projects with students to design or recreate materials that have been published, but they tend to be then too small scale for what we want. So we want to create engineering systems, and so we still need, a certain scale to our materials. And sometimes these materials are exotic. They exist in the lab somewhere, but at a scale that's just not realistic for us.
And the last question I have is with regards to the actuation method. Are there other actuation methods than applying heat to these materials? Or are there other ways to apply the heat to the materials than heating them up?
Yeah, so we've used a lot the shape memory polymers, and that's something now we know how to work with. So with the temperature ones, so basically you can use a water bath is great consistency. It's not the water, it's the heat distribution. In the testing machine we have, the Instron, it's a heated chamber. If it's something that fits in that, that's good as well. And then with some current work, they're going back to some experiments also with heat lamps, because then also you have the directionality of the heat that you can use. We'd like to do more, look at other materials though, and that's a current direction now. So other ways to actuate the materials.
Could mechanical heat would be used as well, for example, when you are launching a satellite into space and then it will deploy its own solar powered component so it can continue further?
Yeah, I think with the solar panel, the idea was the heat came from the sun. Is that right, Tim? Yeah.
Yes, basically. Yeah, that was so it was around the same temperature actually. So it was around 40 degrees Celsius.
Yeah.
So
we had some other work that it was also Thomas Lumpa that he did in collaboration with Dave in Toronto. I can't remember his last name. And there he did some 3D prints, and then he used coils. So he added onboard heating onto the designs themselves using, I can't remember which metal coils that were then heated. Is that what you mean by mechanical heat?
Yes, or just using the power of, for example, for the cars, they would to some extent heat up from the engine inside, as it works harder when they go faster.
Yeah, we didn't look at that. So in the case of the car, we had a project with a company here looking at more pressure distributions on the panels in a car, and using the pressure that would come from driving the car as an actuation method. So that's something we did look at as well. Yeah. I think, I mean, it's really, if you have the right material, then you just think, what does it activate to? And then see what's in the environment that we can use. That's the goal, that you use, whatever's available, really.
Okay, thank you very much. And thank you again very much for your talk. And now I will welcome our second speaker, Tim. And Tim is a Kamal Salam assistant professor at the University of Houston. Since joining the University of Houston in September 2021, he established the Architected Intelligent Matter Laboratory to explore the notion of intelligent metamaterials. In particular, he aims to design materials that can be either transformed their shape or their physical characteristics on demand. With such metamaterials, his goal is to provide a bridge between passive materials and powered robotics. Previously, his road to engineering science was as an undergraduate student in the University of Toronto, and his master's was in civil engineering from Delft University of Technology, and his PhD in mechanical engineering from ETH Zurich, where he received the ETH medal in 2018, and he was most recently a postdoctoral scientist at EPFL. And Tim, the floor is yours.
Thank you so much for the invitation. So yeah, so I'm going to talk a bit more on the so we saw a lot of deployable structures. And in my postdoc, I worked a little bit on how to rationalize this deployment, like what kind of material system we need in order to deploy to the structure that we want. So these are two, one of them is actually really recent works that we did. And in all of these works, we're always trying to do this matching. We're trying to find a structural material system and then abstract their deformation so that we can use some sort of mapping to go from 2D to 3D, or to go from one 3D state to another 3D state. So in my PhD already, we started to look at this with Kristina, actually, over the course of a summer, to see if we can use Chebyshev net to calculate exactly how much we need the diagonals of each square elements to lengthen or contract in order to get a predictable Gaussian curvature. So that's the first work I did in that topic. And then moving to my postdoc time, we started looking at conformal mapping to be able to abstract this deformation. But then, of course, we need material systems that can expand isotropically. And lastly, we started looking at anisotropic contracting or lengthening. So this is a prototypical system. We have these air channels, and when you inflate these air channels, the lateral direction contracts because it goes from, let's say, the length to the diameter, but whereas the length of the tubes don't really change. This is kind of exactly the reverse of a liquid crystal elastomer channels, which lengthens in the length direction and the diameter doesn't really change. So these are kind of material systems that we can abstract their deformation geometrically. Then we can kind of do away with the material systems at the first stage and just look at the geometry. So today I'm going to mainly talk about conformal mapping. So in this conformal mapping system, we have a target surface in mind, and then we're able to flatten this into the 2D while calculating exactly how much locally it needs to contract or expand. So in this example of the target surface, you can see the purple areas need to expand more than the yellowish areas. And using the exact same kind of differential geometry concept, we're able to come up with two different material systems, actually more than two, but these are the two I worked with. So one uses a kirigami cutting of a rubber sheet to go from the 2D to the 3D state in a bistable kind of fashion. So when it's in this 3D state, it can stay in that 3D state. And the second is a very recently, it's still not published, but I think I can talk about it now, work in SIGGRAPH of this year, which uses umbrella mechanisms to go from a very compact yet 3D state to a much larger surface to a 2.5D state, even though the underlying algorithm is actually really similar. So to talk about the first one first, bistable auxetic surface structures. And these are my collaborators and advisors at EPFL. And we start looking at the regular linkage deployable systems that was done before I arrived. So this requires, it's a linkage system with triangular elements, and we need some sort of actuation mechanism to make it go from 2D to 3D state. And there's always the lingering question of what happens at the boundary. And with bistable stable auxetics, we pretty much have seen this already. So with a regular linkage, you can expand to a factor of 2 in length. Yet with the bistable triangular auxetics, even though the base material is exactly the same, it's a rubber sheet, when you expand this, it stays expanded. And you have to apply mechanical force to have it go back to the original state. But of course, because the expansion ratio is the same everywhere, then you just get a bigger sheet. So my question is, can we design a planar surface that encodes its desirable 3D state and have it deployed to that stable 3D state? And then we can define the mechanical characteristics in that 3D state. So the answer is more or less yes. So let me just show you the results first before we discuss further. So this was a planar sheet that was laser cut using just natural rubber, and we're able to just using inertial forcing have it deployed to the 3D state. So first, what is auxetics? I'm sure most of you are familiar with this already, but just to reiterate, a normal material when pulled contracts in the other direction. So we can define the Poisson's ratio as roughly the difference between these deformations. And then we have materials that has a negative Poisson's ratio. So when tension is applied in one direction, it also expands to some degree in the other. And then we have materials that has exactly a -1 Poisson's ratio. So we can deform exactly the same amount in both directions. And fortunately, we see that this regular triangular linkage does exactly this. So if we look at each hexagon as if it's a solid state, solid element, it exactly expands isotropically in a Poisson's ratio of -1 fashion. So let's look at the unit cell geometry of the actual cutting pattern. And we can abstract this into a hexagon featuring 6 mirroring triangular elements with these cuts. And we can parameterize this using, so focusing on the triangle, we can parameterize the geometry using T and theta. And then we look at the rotation of the inner triangle to establish the sort of deployment. By changing theta, you're actually changing the orientation of the cut line, therefore making the inner triangle smaller and smaller. And then with the changing T, it does exactly the same thing. So just by intuition, you can see that the smaller the triangle is, the less expansion we're able to get. So if the original length is L, we can, through kinematics, calculate exactly or predict exactly what the expanded state is. And we can denote this as delta. So just through some equation manipulation, really, we can calculate the expansion ratio at the stretch, which ranges from 1 to 2. And what's interesting, if you look at the color map, is that there are some isolines, which means that there are different parametric combinations that give you the exact same stretch factor. So now we have an additional variable to play with. And we turn to mechanics to answer which unit cell we should pick to get us the expansion ratio we want. So to study the mechanics of these unit cells, we first tried to do an experiment. So building this very complex experimental setup that replicate this periodic boundary condition, we're able to mechanically test the expansion behavior. And this was quite successful in terms of getting the final state, but it's not very successful in getting the intermediate forces because each unit cell kind of snaps at a different time. So when you look at the force displacement curve, it's a mess basically until the very end. And this is not exactly what we need because we need to know the behavior of each individual unit cell at all stages of the string. So we turn to FEM and we notice that there's a quantifiable string that happens at the middle of the expansion, which I denote here in red. So these red regions are actually the stretch of the material. And this red region closes up once we fully expand the unit cell. It closes back down to completely kinematically compatible state. So we built our own basically unit cell simulator that attempts to minimize the total energy of the system by applying a average deformation gradient. Then we're able to calculate. So here's the string energy versus string diagram of the simulation of the FEM. So you can see there's two local minima in the string energy landscape, thereby indicating there's definitely two stable equilibrium states. And since we can easily differentiate this curve, we get the force versus strain diagram that we typically see of a bistable system. So now what do we pick, right? Like knowing the mechanics of the unit cell, we have different criteria that we can use to pick our most ideal unit cell for the purpose. And so first we can see that the strain of the hinges are playing a significant role in determining the stiffness of the structure. Okay, so the first choice we have is the difference energy between the unstable equilibrium, so some sort of intermediate state, and the second state, which is the deployed state. And the second we can optimize for is the slope at the second equilibrium state. So this is exactly the kind of the tangent modulus of the system at that point. And this will give us as stiff of a system as we need in the deployed state. So that's what we're going to use. And unfortunately, I suppose, if we plot the contour map with these two quantities in mind, the maxima doesn't occur at the same place. So by maximizing for one, we kind of have a trade-off with the other. But that's okay. So we choose stiffness as our criteria for picking the unit cell that we need for the purpose. So now we go to the conformal mapping bit of this, right? As I said, if I tile the same unit cell everywhere, then I just get a planar expansion of the structure, which is not exactly what we need because we already know how that works. But now, taking inspiration from cartography, where we can map a globe down to the planar surface, and you see, due to the distortion, we have Antarctica and north of Canada being much bigger than what it actually looks like. We know that we need to change basically the area of each of these squares without changing the angles between the local elements. And if we can satisfy this condition, then we say the deformation is conformal, and we can exactly map, we can calculate the Gaussian curvature based on the difference in the length change of neighboring elements. Okay, so we have a generative algorithm in mind. Given an input surface, we first calculate the conformal factor that allows us to flatten this into the planar state. So in this case, I'm using light green as a lot of expansion and blue as almost zero expansion. And then we can look up in our pre-computed table to find the parameters that give us that particular scale factor. And from these parameter combinations, we find the unit cell that has the stiffest behavior. And then we tile them back into the planar state with the different parameters, triangles tiled together. And then we can easily deploy this into the 3D state. And one thing to note is the boundary condition, right? The boundary is largely free. So except very limited places where we do need a bit of support, otherwise it kind of flattens due to isometric deformation. Otherwise, the structure is freestanding. And with a simple example of a spherical cap, we intuitively know that we need the middle of the spherical cap to expand more than the edges. And we can vary basically whether to say the middle expands a medium amount and edge expands none at all, which means we can clamp the edge if we want to, or the middle expands a lot and the edge expands around the medium amount. And deployment, so this material is not as smart or functional in any way, so we need to use our fingers to deploy this. Fortunately, the snapping of one unit cell kind of triggers the snapping of the neighboring unit cell, and the deployment remains quite easy. And of course, we can use photogrammetry to construct the 3D geometry, or we can use other techniques like CT scanning, for example, to get a more accurate view of the geometry. But either way, it gives us the structure that we need. And we can, of course, change the topology of the system, right? We can have a target surface that has a cylindrical topology, and we still fabricate this flat, and then we'll glue the seam together prior to deployment, because we know the triangles are going to rotate in a compatible manner. So we have a cylindrical system first, and then we deploy this into the vase shape that we wanted. There's other techniques that we can use. Since the Gaussian curvature is controlled by the change in length between neighboring elements, of course, we can have different contractions happening between the neighboring elements to have a porous planar state that deploys by contracting into a more or less continuous 3D state. And of course, we can make more complex geometries too. Keep in mind that the fabrication, we kind of do this because the fabrication is so simple. We just take a commercially available rubber sheet and we just laser cut this, and we can produce these sheets almost in mass. And what's next? So this is a very good tool to use because it's scale invariant. As long as we can satisfy the expansion ratio, then we can make this as big or as small as we want. And so currently I'm working on figuring out how to actually simulate the deployment of a whole sheet. And then we're trying to figure out how do we make this much smaller, or how do we make this much bigger? So for deployment, it's a bit tricky because each unit cell in itself is bistable. So we have a lot of negative stiffness areas that we need to consider. And so far, we have limited success in deploying arbitrary structures. And the next techniques that we may use is to abstract the mechanics as well of each unit cell into a continuum element. And lastly, we did some preliminary tests in the mechanics of these structures. So keep in mind, during the design, we don't consider boundary conditions at all. So of course, this has to sit on something. So by placing a dome structure on the table and applying a load at the apex, we're able to measure the reaction force. And judging by how predictable it is, I think it is actually doable to actually figure out these experimentally, numerically. And lastly, so how do we make this much smaller? As I said, because it's scale invariant, we can totally use techniques in the micro photolithographic arsenal of using wafer technology to make these. And how do we deploy this autonomously? So using what Kristina has mentioned about 4D printing, how do we deploy this without using my hand? And lastly, how do we functionalize this to achieve an engineering kind of application? So these are some of the future directions for this project. And now I'm going to move and talk a little bit about the newest work we did, which is, like I said, based on the exact same technique. But as you can see, this is a 1-to-1 scale geometry here. The expansion ratio we can achieve with this is much, much bigger. In fact, it's, as you will see, infinite. So we call this umbrella meshes because we're literally connecting umbrellas one next to another. So the unit cell mechanism is relatively simple. If you can use our umbrella, you can see we're trading the height of the umbrella to, sorry, let's see if this plays. It's a bit slow. There we go. We're trading the height of the umbrella to the area that it covers. So of course, if we tile the same umbrella next to each other, we get a planar expansion as well. But if we tile two umbrellas of different sizes, heights next to each other, then we get an out of plane deformation, just like we do with the bistable structures. And what's interesting is the footprint of the umbrellas when they're contracted are exactly the same. It's just the height that dictates how much it expands. And due to the incompatibility, there's elastic deformation that's happening during the expanded state. And we can exactly calculate how much they should expand kinematically relatively easily just by using the height as the input parameter and calculating what the expansion ratio is. And for deployment simulation optimization, again, we have several contributing energies that we need to account for. The first is the elastic energy of the rods. We model them as discrete elastic rods. And the second is the potential energy of the deployment force that we do need to apply to have the whole system start deploying. And there are several constraints that we must use both in physical fabrication and in simulation to ensure the angles of rotation does not exceed a certain bound. And the last is a little bit of a fictitious energy that we use to attract the deployment towards the target state. Of course, we weigh this to near zero near the deployment. And we minimize the total amount of energy by using the height as the optimization variable. So the design pipeline, again, this will look reminiscent of what we had before. We first to conformally flatten the structure to the planar state. We overlay a grid of triangles and we assign the scale factor to each one of these triangles. And this is the entire pipeline of the system. Once we do the triangle assignment, then we have an initialized system, which we continuously modify through a gradient-based optimization to get the final structure. And as I said before, the expansion is theoretically unbounded because we can have heights as big as we want. And one demonstration of this is to cover more than a hemisphere. And you can see in this case, we're able to cover almost 3/4 of a total sphere by having an uniform expansion of around 28 times around the apex of the sphere. So of course, the height cannot go to infinity in real life, so we cannot actually have a full sphere, but we can approach that much more rapidly than what we did before. And one remaining kind of thing we noticed almost by chance is that when deployed, the structure is stable. So this, from the get-go, wasn't what we were aiming for, but it does exhibit a local minimum in the elastic energy landscape, just like what we did before with the biaxial structures. So when we deploy the sphere, for example, the structure goes into a stable 3D state. And we don't exactly know why yet. So this is something that we're still looking into. For positively curved structures, we have an intuition, but this also happens for negatively curved structures. And here are some deployment simulations of complex structures like C. And now we move to the physical design of the unit cell. We cut these scissor mechanisms and attach the top and bottom plate. And you see this is the transformation that happens through these live hinges or elastic joints. And the fabrication is, again, planar and very simple. So we use a milling tool that's able to fabricate using polypropylene as material. And we assemble these manually to create the compact state. And then we deploy this into the 3D state. Yeah, here's the deployment of the sphere. So you can see the scale of the model relative to human being. And it takes 2 people to deploy the sphere into its final deployed shape. And so lastly, I want to mention the reason we started this project is to take advantage of 3D printing. This is maybe something that was missing from the talk. And so now I'm experimenting using selective laser sintering to make these 3D umbrella structures. And we have some success in deploying a hemisphere again. So thank you so much. And I'll answer any questions you have now.
Thank you very much for your talk. And we have a couple of questions from the audience.
Sure.
And for the start, there is a couple of questions still related to the past projects that Kristina was mentioning.
Sure, yeah.
But perhaps you could help answer those as well. So for the bistable morphing structures, are they limited to be bistable, or could they go into multiple configurations? I guess we could also extend this question to the auxstatics, if they could potentially have 2 or 3 configurations as well.
Right. Yeah, that's a good question. Let me go back to the very beginning of the talk. So this exactly answers your question. So with many, let's say, bistable units tiled next to each other, each unit cell can snap without the neighboring snapping. So these are, in fact, all the intermediate states. Of course, we didn't design for them, but they are stable states that we can achieve. But in this project, we explicitly designed for a planar structure to transform to 2 different global structures, 3D structures that have 1 set or 2 sets of the bistable units triggered. So the diagonal length goes from length 1 to length 2 or 3. And then globally, of course, they go into 2 different structures. So this is just a picture of a unicell that's it's the exact same unicell that goes into the 2 shapes below. Yeah. So for the auxetic sheets, that's something where we don't know how to do yet. That's something we're looking into. Yeah.
And how consistent is the fabrication process of the bistable triangular linkages via laser cutting? Does it sometimes happen that the joint is cut through or not cut enough for deployment?
Right. So that's something. So at the beginning of the project, we thought we need to make the joints as thin as possible to maximize this bistability. That didn't turn out to be necessary, which was a bit counterintuitive. So we ended up, of course, at first, it was a trial and error thing. We tried to minimize the hinge thickness to our particular laser cutter so that it never cuts through, but it's still very small. But the bistability, once we actually made the system and deployed it, was never in question. It's in fact much easier to deploy from the planar state to the 3D state than it is to go back. So as I said, when we deploy the opening of one unit cell triggers the opening of the other. But when we try to put it back, we kind of have to hold each unit cell in place and manually trigger each unit cell separately to be able to get it back. So global bistability was always guaranteed. And now we know that the thicker the hinges, the stiffer the system is. So we actually want to increase the thickness of the hinges to get more mechanical stability. Yeah.
And is there an upper size limit for these triangle structures such that they can still hold some weight?
Right. So that's where the stiffness comes in. We don't consider, as I said, during the design pipeline, there's no boundary conditions. So we don't consider gravity or any other forces in the system. So as the bigger it is, the bigger kind of overhang we have, the bigger gravity is going to deform the structure. And as you know, less curvature there is, the more deformation we're able that will happen. That's why, in a way, I'm aiming to make it smaller, right? So by having unicell triangles that's about 10 micrometers, then we have a whole other set of mechanical forces that we need to consider that's not gravity. So we're able to use things like surface tension to be able to deploy the system. Yeah. In a larger scale, I'm not sure. So in a larger scale, we discussed when I was still at EPFL to make a pavilion using not a monolithically fabricated system, but we have like metallic copper plates and we have hinges that's actually hinges. And then we're able to make it like a meter long big system that's much stiffer. Yeah.
Because then it would get much more stiffness in through the metal parts.
Right, it would be much stiffer, but I'm not sure if we can deploy them. Right, because we still need to overcome this bistability, which at a big enough force becomes unsafe for people to do. Right, so we may have to construct them in the deployed state.
Yeah. And the last question that I have is for the last project, or also for the previous one. To achieve a target shape, you first flatten it in to the plane and then optimize from there. So what would happen if your shape is symmetric? How do you break the symmetry if you would like to have some bump one way or the other?
Right. Oh yeah, sure. So you mean, yeah, okay, that's a good question.
For example, a perfect hemisphere could go up or could go down.
Right. So for the first project, we don't. So indeed, I don't have any. So for example, this one, it could go up or down. There are a lot of there's more than one isometric deformation modes that we don't consider. So we do need to mechanically kind of help it to go into the right state because we can't control the mean curvature of the system. But that's one feature of the second project, which we are able to do this because go to that particular thing. Because we have the midplane, which is what the conformal mapping tells us how much it needs to expand. And then we have the height above the midplane and the height below the midplane. We could set them to be the same to achieve, the Gaussian curvature that we needed, but we don't have to. So right now, we do consider mean curvature and adjust the difference between the top height and the bottom height, such that it only deploys into the one direction. So in this case, for a hemisphere, you can imagine the height above the midplane is bigger than the height below the midplane. So in a sense, we kind of have two layers of structures that gives us an intuition of mean curvature in addition to Gaussian curvature. Yeah.
Oh, very interesting. So this way you can program both sides at the same time, and therefore there is not asymmetry anymore.
Exactly, right. Yeah. So we could have up bump and low, two bumps in two directions. Yeah.
Nice. So thank you much for staying around and answering the questions from the audience.
Yeah,
and now we will move into the free discussion that is not recorded anymore. So
okay, sure.
we invite anyone to join us on the Zoom link, and thanks everyone for your attention.